Good morning, everyone. I'm Caleb Emmanuel Frias from STEM12A, and today I'm gonna solve some capacitance and dielectrics problems. Chapter 24. A capacitor is made from two hollow coaxial iron cylinders, one inside the other. The inner cylinder is negatively charged and the outer is positively charged. The magnitude of the charge on each is 17.5 picocoulomb. The inner cylinder has a radius of 0.450 millimeters. The outer one has a radius of 6.20 millimeters, and the length of each cylinder is 21 centimeters. First is, what is the capacitance? What applied potential difference is necessary to produce these charges on the cylinders? First, we're gonna find the capacitance. So first of all, we're gonna list the given values first, and then we're gonna use the capacitance formula, and then you're gonna substitute the A in the formula to the area of the coaxial cylinder. After that, you just substitute the given values in the formula, and then you're gonna get 4.45 times 10 raised to negative 12 Faradays. After that, we were asked to find the potential difference. So in order to do that, you're just gonna use the capacitance is equal to Q over V, and then you just use algebra in order to focus the formula to finding the volts or the potential difference. And then after that, you just substitute the given values, and the capacitance, you use the one that you solve from the first problem, which is problem A, and then you're gonna get 3.93 volts. Next problem. The dielectric to be used in a parallel plate capacitor has a dielectric constant of 3.20 and a dielectric strength of 1.5 times 10 raised to negative 7 times 10 raised to 7 volts per meter. The capacitor is to have a capacitance of 1.45 times 10 raised to negative 9 farads and must be able to withstand a maximum potential difference of 5200 volts. What is the minimum area the plates may have? So we will find the minimum area the plates of the capacitor may have. As usual, we're gonna use the given values. And then after that, we're gonna use the formula for the area of the parallel plate capacitor. And then for the dielectric strength, we just equate it to the volts over the thickness, which is denoted by T. So in the dielectric strength formula, you just substitute the given values, and for the thickness you're gonna get 3.5 times 10 raised to negative 4 meters. And for the area formula for the parallel plate capacitor, you just substitute the values because you already found D, which is the only one missing before. So after that, after substituting everything, you're gonna get 0.018 meters squared. So next problem. Electronic flash units for cameras contains a capacitor for storing the energy used to produce the flash. In one such unit, the flash lasts for 1.43 times 10 raised to negative 3 seconds, with an average light power output 2.9 times 10 raised to 5 watts. First problem. If the conversion of electrical energy to light is 96% efficient, the rest of the energy goes to thermal energy. How much energy must be stored in the capacitor for one flash? Next problem. The capacitor has a potential difference between its plates of 110 volts. When the stored energy is equal to the calculated in part A, what is the capacitance? So we were asked to find the energy stored in the capacitor for one flash. So as usual, we're gonna list the given values at the right side, as you can see, and we go also write the power formula if in case you forgot what it is. And also we're gonna use algebra to focus it in finding the energy. So you just substitute the given values in the formula, easy. So you're just gonna get E is equals to 414.7 joules. And since it's asked for 96% efficiency, you divide the 414.7 joules by 0.96, which will get 432 joules. Next problem, we were asked to find the capacitance. So the formula for capacitance, we will get it from the energy formula, and you just use algebra to focus it in finding the capacitance, as you can see at the bottom left. And since you already found the energy from the problem A earlier, you just substitute it, and also from the other given values in the formula, and then you're gonna get zero point zero 0.07 Faradays for the capacitance. Thank you for watching, and God bless you.